You wake up every morning surrounded by matter, your coffee mug, your phone, the air you breathe, even your own body. It's all made of the same fundamental building blocks that have existed since the dawn of time. But here's something that should keep you up at night. According to everything we know about physics, none of this should actually be here. Not your coffee, not your phone, not even you. See, when the universe began, it should have created equal amounts of matter and antimatter. And when those two meet, they don't just cancel out. They obliterate each other completely, leaving nothing behind but pure energy. The entire cosmos should be an empty void filled with nothing but radiation. Yet here we are, living proof that something went catastrophically wrong with that plan. For decades, scientists at CERN have been chasing this mystery with some of the most sophisticated machines ever built. They've smashed particles together at nearly the speed of light, trapped antimatter in magnetic bottles, and even figured out how to move the stuff between buildings like it's just another lab sample. But the more they discover, the more puzzling everything becomes. And now, something truly strange is happening. Recent experiments have uncovered behaviors in antimatter that nobody saw coming, tiny violations in the laws of physics that might finally explain why anything exists at all. But they've also raised questions that threaten to shake the very foundations of what we thought we understood about reality. So what exactly is going on behind the scenes at the world's most advanced physics laboratory? Why are scientists more confused than ever, despite having access to billion-dollar detection systems? And could these latest discoveries be pointing towards something completely new, something that goes beyond everything we thought we knew about the universe? The story begins at the very moment everything started. When the Big Bang erupted into existence, our best theoretical models tell us it should have produced matter and antimatter in perfectly equal quantities. For every single proton that came into being, there should have been an antiproton. For every electron, a positron. This isn't just speculation or educated guesswork. This is what the mathematics of particle physics demands. But here's where things get interesting. When matter and antimatter particles encounter each other, they don't just bump into each other like billiard balls. They annihilate instantly, converting their entire mass into pure energy according to Einstein's famous equation. No leftovers, no survivors, no second chances. It's the most complete form of destruction possible in the universe. Look around you right now. Everything you can see, touch, or interact with is made of regular matter. Stars, planets, galaxies, your morning breakfast. There's no visible antimatter just floating around in space. That's incredibly weird, because it shouldn't be possible. If the universe started with equal amounts of both, and they destroy each other on contact, we should be living in a cosmic graveyard, filled with nothing but leftover radiation. But somehow, in those first few microseconds after the Big Bang, something tipped the scales. There was a tiny, almost impossibly small excess of matter over antimatter. We're talking about maybe one extra particle for every billion pairs that annihilated each other. That minuscule surplus is literally everything. It's what became the raw material for every atom in every star, every planet, and every living thing that has ever existed. The rest, the overwhelming majority of both matter and antimatter, wiped each other out in a cosmic holocaust of mutual destruction. We're essentially living in the debris field of the universe's greatest catastrophe. And nobody knows why that tiny imbalance occurred in the first place. Physicists have a fancy name for this puzzle. They call it the Barrian asymmetry problem. Translated into plain English, it's asking, where did all the antimatter go, and why did regular matter win the cosmic lottery? It's not just an academic curiosity either. If we could figure out what caused that original imbalance, we'd be one step closer to understanding why anything exists at all, instead of just empty space filled with photons. That's precisely why CERN built experiments like the Large Hadron Collider. These aren't just massive machines designed to smash particles together for the sake of destruction. They're precision instruments built to study the tiniest possible differences between matter and antimatter, Because maybe, just maybe, if scientists can catch antimatter behaving even slightly differently from its matter counterpart, they'll discover the clue that's been hiding in plain sight for billions of years. And this year, they finally spotted something unusual again, something that shouldn't be happening according to our current understanding, but clearly is. Let's dive into something called CP violation, because this is where the physics starts getting genuinely strange. CP symmetry is built on a fundamental idea that sounds almost too simple to be important. It says that if you take any particle and flip it into its antimatter version, then also reverse its spatial coordinates, like you're looking at it in a mirror, the laws of physics should behave exactly the same way. That's supposed to be an ironclad rule of the universe. At least it was supposed to be ironclad. But for decades now, scientists have known that this rule has cracks in it. Back in the 1960s, physicists discovered tiny violations of this symmetry in certain particles made of a quark and an antiquark. Even though these violations were incredibly small, they were significant enough to suggest that matter and antimatter don't always behave as perfect mirror images of each other. But here's the catch: those particles, called mesons, decay far too quickly, and their CP violations aren't nearly strong enough to explain the massive imbalance we observe throughout the universe. Scientists needed to find something bigger, something more substantial. They needed to look at baryons, the same class of particles that includes protons and neutrons, the actual building blocks of all the matter we see around us. And this year, it finally happened. CERN's LHCb experiment, which specializes in hunting for differences between matter and antimatter, announced they had observed CP violation in a particle called the lambda B baryon. This is a heavy particle constructed from 3 quarks, just like a proton, but with different types of quarks inside its structure. For the first time ever, physicists witnessed clear evidence that these baryons don't behave identically to their antimatter twins. That's a genuinely big deal in the world of particle physics. The asymmetry they measured wasn't enormous, only about 2.5%, but in the realm of subatomic particles, that's enough to set off alarm bells throughout the scientific community. The statistical significance of this discovery reached 5.2 sigma. If you're not familiar with the technical jargon, that basically means the chances of this being a random fluke are less than 1 in several million. In scientific terms, it's as close to certainty as you can get. This discovery is real, and it's not going away. Now, this doesn't mean scientists have suddenly solved the antimatter mystery. We're not there yet, not by a long shot, but it does provide a new direction for research, a new class of particles where the differences between matter and antimatter might be more pronounced than previously thought. And if those differences can scale up, even just slightly over cosmic timescales, they could potentially explain why matter survived the early universe, while antimatter largely vanished. It's one of those pivotal moments in physics where the door doesn't swing wide open, but it does crack just enough to let some new light shine through. And suddenly, people throughout the scientific community are paying attention again. Because if baryons like the lambda B behave differently from their antimatter counterparts, then maybe protons and antiprotons do too. Maybe the fundamental building blocks we're all made of aren't as perfectly symmetric as we've always assumed. And maybe that asymmetry is the key to understanding the universe we actually live in, rather than the empty wasteland it should have become. But that discovery represents just one piece of a much larger puzzle that's currently unfolding at CERN. Because while the Large Hadron Collider has been busy studying high-energy particle collisions, something even more extraordinary has been happening in another part of the facility. Scientists there are attempting to do something that sounds almost impossible. They're trying to put antimatter in a truck and drive it across town. You probably don't think of antimatter as something you can just load onto a vehicle and transport like any other laboratory sample. But that's exactly what CERN has been working toward, and they've actually succeeded. For the first time in human history, Scientists have successfully moved a cloud of antiprotons across the CERN campus using a specialized mobile containment system. They constructed what amounts to a high-tech box capable of safely containing charged particles, then drove it approximately 4 kilometers across the facility. This proved that they could potentially transport actual antimatter the same way in the future. But why is this such a monumental achievement? The answer lies in just how incredibly difficult antimatter is to handle under any circumstances. Antimatter isn't just rare or expensive, it's absurdly challenging to work with, because the moment it comes into contact with regular matter, it annihilates completely. There's no second chance, no do-over, no putting the genie back in the bottle. It's gone, releasing massive amounts of energy in the process. You can't store it in a glass container, or freeze it, or shove it into a metal tank like you would with any normal substance. Instead, antimatter has to be suspended, essentially levitated, inside carefully controlled magnetic fields within a perfect vacuum, all contained within a meticulously engineered trap. It's like trying to carry a droplet of pure sunlight in your bare hands without getting burned. So why would anyone want to take that kind of risk? The reason comes down to precision. While CERN's antiproton decelerator is excellent at generating and studying antimatter, the entire facility is surrounded by powerful magnetic fields from nearby accelerators and other scientific instruments. Those fields can subtly interfere with the delicate measurements scientists want to make, introducing noise and uncertainty into their data. So researchers developed a method to transport these charged particles to a quieter, more controlled laboratory environment. Specifically, they wanted to move them to a facility in Germany that offers better electromagnetic shielding and significantly less magnetic interference. That's what this mobile antimatter trap was designed to accomplish, and it worked flawlessly. The device managed to keep a cloud of antiprotons stable and completely isolated for more than 12 hours throughout the entire journey. The fact that they could maintain these particles in a secure state during actual transportation opens up possibilities for entirely new types of experiments that were previously impossible to conduct. Soon, scientists will be able to test how antimatter behaves in different environments, not just at CERN, but in laboratories across Europe and eventually around the world. This changes everything about antimatter research because it's no longer confined to studying these particles only where they're produced. It's about preparing to use antimatter, transport it, and push the boundaries of where we can take it for scientific investigation. We've transitioned from generating antimatter in fixed detection systems to proving we can transport antiproton substitutes safely over significant distances. That might sound like a small step, but in the world of experimental physics, it represents a massive leap forward. It means new collaborations between institutions, new technologies for containment and transport, and far more precise tests of one of the strangest substances in the known universe. And all of this progress is happening while another group of scientists at CERN is asking an even more bizarre question. What if antimatter doesn't fall the same way regular matter does? What if gravity itself treats antimatter differently than everything else we've ever studied? It sounds like the kind of thought experiment people post online as shower thoughts. If antimatter is the opposite of matter, does it fall upward instead of down? But at CERN, this isn't a joke or a philosophical discussion. It's an actual scientific experiment with real implications for our understanding of fundamental physics. This represents one of the strangest and most overlooked problems in all of physics. How exactly does antimatter respond to gravitational forces? If you were to drop a ball made entirely of antimatter, would it fall toward the ground like a regular ball, or would it do something completely unexpected? Would it fall more slowly, more quickly, or in the opposite direction entirely? That last possibility seems unlikely based on our theoretical understanding, but until recently, nobody could say for certain because the experiment had never been performed. In 2023, Two major experiments at CERN finally conducted detailed tests to find out once and for all. The first was called Alpha G, an extension of earlier alpha experiments. The second was G bar, which stands for gravitational behavior of antihydrogen at rest. These names might sound highly technical, but what they were attempting to do was remarkably straightforward. Create a small cloud of antihydrogen atoms, release them, and observe what happens under the influence of Earth's gravity. For this to work properly, the atoms had to be electrically neutral, with no net charge, because any electric field would interfere with the gravitational measurements. The challenge was isolating pure antihydrogen and keeping it suspended perfectly motionless inside a vacuum chamber using only magnetic fields. Then they had to release it and carefully watch what gravity did to these incredibly fragile particles. It sounds simple in principle, but the execution was extraordinarily complex. These antihydrogen atoms are incredibly delicate and fragile. The experimental conditions had to be absolutely perfect, and the total fall distance was only a few centimeters. That's it. Scientists were essentially trying to detect the gravitational behavior of what amounts to atomic ghosts, but somehow they managed to pull it off. And here's what they discovered. Antihydrogen falls downward, just like regular hydrogen. According to the Alpha G results from 2023, it accelerates under Earth's gravitational field in the same direction and at a rate that's consistent with normal matter, at least within the precision limits of their experimental setup. G-bar continues working towards similar measurements, aiming to confirm these findings with even greater accuracy. But there's something intriguing buried in the data, just a hint that the acceleration might be slightly different from what we'd expect. Not enough to completely overturn the laws of physics, but enough to make scientists look more carefully at the numbers and wonder if there might be something more complex happening beneath the surface. A few results from other gravitational studies were also slightly off from perfect predictions, though still well within the margin of experimental error. Nothing conclusive, nothing that would make headlines around the world, but not perfectly ordinary either. And that's what makes these measurements so fascinating from a scientific perspective. If antimatter does behave even marginally differently under gravitational influence, it could fundamentally reshape everything from quantum field theory to general relativity. Einstein's equivalence principle, the foundational idea that gravity affects all objects the same way regardless of their composition, had never actually been tested on antimatter until these recent experiments. And while the early results suggest that antimatter follows the same gravitational rules as regular matter, physicists are far from finished with their testing. Because if they can detect even a tiny deviation, something as small as 0.1%, that would be sufficient to shake the very foundations of modern physics. So they're conducting additional tests, refining their measurement techniques, and increasing the sensitivity of their detection equipment. Because in this type of science, it's not always the dramatic discoveries that matter most. Sometimes it's the microscopic differences that reveal when something fundamental is broken in our understanding. And when something breaks in physics, that's precisely when the most interesting discoveries begin to emerge. But while all of this antimatter research continues across CERN's various facilities, including the gravity experiments, precision spectroscopy, and mobile transport systems, there's yet another antimatter mission preparing to attempt something even more ambitious. They're not just studying antimatter in isolation anymore. They're planning to deliberately crash it into some of the most unstable atoms in the universe. So where does all this antimatter actually originate? You can't mine it from the ground, and you definitely won't find it lying around anywhere in nature. At CERN, antimatter is manufactured in one of the most sophisticated and advanced sections of the entire complex, something most people have never even heard of. It's called the antiproton decelerator, abbreviated as AD, and it does exactly what the name suggests. It's a machine specifically designed to slow down particles that nobody can physically touch. Here's how the entire process works. First, high-energy protons get fired into a block of extremely dense metal. This collision creates a shower of exotic particles, including antiprotons, which are the antimatter equivalent of regular protons. These antiprotons are born moving at tremendous speeds, far too fast for scientists to study them effectively. That's where the antiproton decelerator steps in to slow them down dramatically. We're not talking about a slight reduction in speed either. The system reduces their velocity by a factor of 100,000 or more because you simply cannot study antimatter when it's racing around like a high-speed bullet. You need these particles calm, cold, and nearly motionless. This is where ALINA comes into the picture. ALINA is a smaller circular accelerator that connects directly to the AD system. But instead of speeding particles up, like most accelerators do, it takes them even slower than before. Think of it as a specialized cooling ring designed specifically for antimatter. ALINA can reduce antiproton speeds to just a few millionths of the speed of light, gentle enough that scientists can trap them using carefully controlled magnetic fields. Once they reach these incredibly low speeds, scientists can capture them in highly specialized experimental setups. There's the alpha experiment, which creates antihydrogen and tests its response to gravity. There's base, which compares the magnetic properties of protons and antiprotons with almost unbelievable precision. And there's ASA-CUSA, which studies the internal structure of antihydrogen using advanced laser spectroscopy techniques. Each of these experiments searches for the tiniest possible differences between matter and antimatter, differences that might eventually explain why the universe developed the way it did instead of remaining an empty void. If they discover something, even something incredibly small, it could revolutionize how we think about symmetry, time, and the Big Bang itself. But here's what makes this entire operation so remarkable. This isn't a massive collider smashing particles together at nearly light speed. These are quiet, controlled, ultra-precise experiments that operate more like atomic surgery than demolition work. That contrast perfectly captures what makes CERN such an unusual place. On one side, you have detectors the size of office buildings, where particles crash into each other at unimaginable velocities. On the other side, you have tiny chambers, cooled to temperatures near absolute zero, designed to gently hold just a few antimatter atoms, as if they were made of the most delicate glass imaginable. This is the antimatter factory, not just a single machine, but an entire ecosystem of interconnected experiments. Each one has its own specialized purpose, its own specific questions to answer, and its own piece of the cosmic puzzle to solve. And now this whole system is preparing to attempt something even more ambitious than anything they've done before. They're planning to take that carefully stored antimatter and fire it directly at some of the most unusual atoms in the universe. Unstable radioactive nuclei that exist for only fractions of a second. Because maybe the answers don't lie in simply studying matter and antimatter separately. Maybe they lie in understanding exactly how they interact with each other. That's the ultimate goal of CERN's next major antimatter mission, something called PUMA. You've probably heard of particle accelerators and antimatter containment systems. But now scientists at CERN are attempting something that sounds almost too science fiction to be real. They're going to take over 1 billion antiprotons and bring them face to face with unstable atomic nuclei so rare and short-lived that they don't exist anywhere in the natural world. And they're planning to do this in a location where antimatter has never been before. The project is called PUMA, which stands for Antiproton Unstable Matter Annihilation. It represents one of the most ambitious antimatter experiments ever conceived by human scientists. Here's the basic concept. CERN operates 2 completely separate main research areas. One houses the antiproton decelerator and ALINA, where antimatter gets produced and slowed down to manageable speeds. The other is a facility called ISOLDE, where physicists study exotic atomic nuclei that decay within fractions of a second after being artificially created through nuclear reactions. Normally, these two research areas never interact with each other. Antimatter research stays on one side of the complex. Radioactive nuclei research stays on the completely opposite side. Puma is going to change that separation permanently. Scientists are constructing a mobile antimatter containment system strong enough to hold more than 1 billion antiprotons in a stable, isolated state for hours at a time. This trap will then be physically transported from the antimatter laboratory to Isolde, where those antiprotons will be released in a controlled beam directly onto unstable atomic nuclei. But why attempt something so technically challenging and potentially dangerous? The answer lies in what happens when an antiproton collides with the nucleus of an atom. It annihilates with one of the protons or neutrons inside that nucleus, and the debris from that annihilation process reveals incredibly precise information about the internal structure of the nucleus it collided with. In other words, antimatter becomes a specialized microscope, a probe that allows scientists to peek inside radioactive atoms that are normally impossible to measure using conventional techniques. This type of experiment has never been attempted before, not at this scale, and not with this level of precision. The hope is that by observing how antiprotons interact with these exotic atoms, scientists can learn more about the fundamental forces operating inside atomic nuclei, particularly in regions called neutron skins, where unstable atoms tend to develop strange lopsided shapes that don't follow normal patterns. It could even provide hints about new nuclear physics that goes beyond what the standard model can currently explain. And here's the truly remarkable part of this entire endeavour. This experiment requires moving antimatter between buildings using a truck. That alone represents a significant scientific achievement. It's challenging enough to keep antiprotons from touching anything in a stationary laboratory environment, let alone maintaining their stability through transportation, temperature fluctuations, and mechanical vibrations from a moving vehicle. But if Puma succeeds, it could completely transform how antimatter research gets conducted in the future. Antimatter won't be confined to a single laboratory anymore. It could be transported wherever it's needed, brought to new experiments, new materials, and potentially even new countries for international collaborations. Antimatter might actually become mobile, opening up possibilities for entirely new types of research that haven't even been imagined yet. But despite all this remarkable progress happening across multiple fronts, including CP violation discoveries in baryons, successful gravity experiments, precision spectroscopy measurements, and now mobile antimatter transport, there's still one persistent problem that continues to frustrate scientists. Nothing they've discovered so far has completely explained the central mystery. Why does the universe contain more matter than antimatter? The experimental data keeps improving with each passing year. The technological tools keep evolving and becoming more sophisticated, but the fundamental answers they're searching for still aren't lining up with their observations. You'd think that with everything currently happening at CERN, including the CP violation discoveries, the precision experiments, the antimatter gravity tests, and the billion-dollar detection systems, scientists would have uncovered something significant by now, something that clearly demonstrates where the standard model breaks down, something that finally provides a definitive answer to the antimatter question that's been haunting physics for decades. But that's exactly what makes this situation so frustrating for researchers. Despite all this incredible work and these historic measurements, the laws of physics continue to hold up under scrutiny. When you step back and look at the bigger picture, all these experiments are pointing toward the same uncomfortable conclusion. Nothing they've observed yet is sufficient to explain why the universe overwhelmingly favors matter over antimatter. That CP violation they discovered in baryons is real and genuinely exciting from a scientific perspective. But the numerical values still don't add up to account for the massive imbalance they observe throughout the early universe. The asymmetry they measured is simply too small to explain the sheer scale of matter dominance that exists in cosmic reality. The gravity experiments with antihydrogen have shown that antimatter falls downward like regular matter, at least so far. No dramatic surprises, no strange repulsion effects, nothing that would revolutionize our understanding of gravitational physics. The BASE and Asakusa experiments continue checking for the smallest possible violations of something called CPT symmetry, the theoretical principle that flipping charge, parity, and time together should make no difference to physical laws. But those tests have achieved such incredible precision that any significant deviation would have already generated headlines around the world, and they haven't. It's almost like scientists are chasing a ghost through the halls of CERN. They know something must be out there, some mechanism that tipped the cosmic scales toward matter in the early universe. But every time they think they're getting close to an answer, the experimental data just whispers back, "Not quite, try again." To be absolutely clear, this doesn't mean these experiments represent failures in any way. Far from it. Every single result, even the ones that show nothing particularly unusual, help sharpen our understanding of the universe. Each measurement rules out incorrect theories. Each data point tells researchers where not to look next. They're systematically closing doors so scientists can focus their attention on the ones that remain slightly open. But the reality is that physicists are genuinely puzzled by these results, and they're not trying to hide that confusion from the public. In many ways, that scientific honesty makes the whole endeavour more compelling rather than less. CERN isn't pretending to have discovered all the answers to cosmic mysteries. They're openly admitting that the universe continues hiding something from us, something profound and subtle that we haven't figured out yet. Maybe it's an undiscovered particle that we haven't detected. Maybe it's a fundamental force that we don't understand properly. Or maybe it's a breakdown in symmetry, so incredibly small that it's like trying to hear someone whispering in the middle of a thunderstorm. And that represents the genuine reality of cutting-edge physics research. You can construct the most powerful machines ever built by human civilization. You can conduct the cleanest, most precise experiments imaginable. You can trap the rarest particles in the known universe, and you can still walk away from all that work with more questions than answers. But here's the thing about scientific research, that's not actually a failure. It's evidence that you're pushing against the real boundaries of human knowledge. Because when established rules start breaking down at the edges of what we understand, that's precisely where genuine discovery begins to happen. So for now, the antimatter mystery remains exactly that, a mystery. Scientists have successfully ruled out numerous incorrect explanations. They've dramatically narrowed down the range of possibilities, but that final crucial piece of the cosmic puzzle continues to elude their grasp. And yet it's that very uncertainty that keeps driving researchers forward. Because in physics, confusion and frustration aren't signs that you've reached the end of the story. They're clear indicators that something truly interesting is about to emerge from the shadows. The deeper scientists dig into antimatter research, the more complex the questions become. They've moved far beyond simple theoretical speculation. They've successfully isolated antiprotons, trapped antihydrogen atoms, watched them respond to gravity, and even loaded antimatter substitutes into specialized vehicles for transport across campus. And yet, the fundamental mystery of why the universe contains more matter than antimatter remains as puzzling as ever. Why does anything exist at all instead of just empty space filled with radiation? It's not because scientists haven't been trying hard enough. CERN has constructed some of the most sophisticated tools humanity has ever developed, all focused on getting closer to that one crucial answer, and they're nowhere near finished with their investigations. The LHCb experiment continues operating, searching for additional CP violations in different types of particles. The antiproton decelerator and ELINA systems keep feeding antimatter to various specialized experiments. New ambitious missions like Puma are just beginning their development phases, But none of this research is about trying to prove existing theories anymore. It's about listening very carefully to what the universe might be quietly trying to communicate through these incredibly subtle experimental results. Because somewhere hidden within all this accumulated data lies a hint of something much larger than what scientists have discovered so far, something they've overlooked or misinterpreted. Right now, researchers aren't claiming victory over cosmic mysteries. They're doing something much more difficult and honest. They're publicly acknowledging that the mystery remains unsolved. And in a scientific field that's built on providing definitive answers, that kind of intellectual humility suggests something important. It means they're probably getting close to something significant. Because every time an experimental result comes back showing almost but not quite what theories predict, it pushes human understanding a little further beyond what we thought we knew about reality. And that's exactly where the most important discoveries tend to emerge. So if antimatter keeps refusing to follow the rules we've written for it, that might actually be excellent news for physics. It suggests that those rules are ready to be rewritten, expanded, or completely revolutionized. While all these precision experiments continue at CERN, generating ever more detailed measurements and increasingly sophisticated data, there's something else happening that deserves attention. The scientific community is preparing for what might be the next major breakthrough in antimatter research. New detection technologies are being developed that could identify asymmetries too small for current instruments to measure. Advanced theoretical models are being constructed that might predict where to look for the subtle violations that could explain everything. International collaborations are forming to tackle different aspects of the antimatter puzzle from multiple angles simultaneously, and perhaps most importantly, entirely new experimental approaches are being designed that don't just study antimatter in isolation, but examine how it interacts with exotic matter under extreme conditions that have never been tested before. The Puma experiment represents just one example of this new direction. By combining antimatter research with studies of unstable atomic nuclei, scientists are exploring completely uncharted territory. They're looking for clues in places where no one has thought to search before. But Puma isn't the only ambitious project on the horizon. Other research groups are developing plans to study antimatter under different gravitational conditions, perhaps in space-based experiments where Earth's magnetic field won't interfere with measurements. Some are investigating whether antimatter behaves differently when subjected to intense electromagnetic fields or extreme temperatures. Others are exploring whether antimatter might interact with dark matter in ways that regular matter doesn't, potentially opening up entirely new avenues for understanding the invisible components of the universe that make up most of its mass. These aren't just incremental improvements to existing experiments. They represent fundamental shifts in how scientists approach the antimatter mystery. Instead of assuming that antimatter should behave exactly like matter except for its opposite charge, researchers are beginning to question whether that assumption might be limiting their understanding. What if the differences between matter and antimatter are more subtle and complex than anyone has imagined? What if those differences only become apparent under very specific conditions that haven't been tested yet? What if the key to solving the mystery lies not in the particles themselves, but in how they interact with forces and fields that we're only beginning to understand? These questions are driving the next generation of antimatter research at CERN and laboratories around the world, and they're leading scientists into experimental territory that would have seemed impossible just a few years ago. The technology for trapping, manipulating, and transporting antimatter has advanced so rapidly that researchers can now contemplate experiments that were pure science fiction when CERN first started operating. They can move antimatter between buildings, study its gravitational behavior with unprecedented precision, and prepare to crash it into exotic atomic nuclei that exist for mere fractions of a second. But perhaps the most significant development isn't technological, it's conceptual. Scientists are learning to embrace the mystery rather than trying to force it into predetermined theoretical frameworks. They're discovering that the universe might be far stranger and more complex than anyone suspected, even after decades of groundbreaking research into the fundamental nature of reality. And that realization is opening up possibilities for discoveries that could revolutionize not just particle physics, but our entire understanding of why anything exists at all. The antimatter mystery at CERN isn't just about exotic particles and billion-dollar experiments. It's about confronting the deepest questions of existence itself. Why is there something rather than nothing? What determines the fundamental structure of reality? Are there aspects of the universe so subtle and complex that we're only just beginning to glimpse them? As scientists continue pushing the boundaries of what's possible with antimatter research, they're not just hunting for answers to specific technical questions. They're exploring the very foundations of a physical reality, searching for clues about how the universe actually works at its most fundamental level. And every strange result, every unexpected measurement, every tiny deviation from theoretical predictions brings them one step closer to discoveries that could transform human understanding of the cosmos itself. The story of antimatter at CERN is far from over. In fact, it might just be getting started. Because while researchers have been making these remarkable discoveries about CP violations and mobile antimatter transport, there's another dimension to this mystery that most people never hear about. The human side of what it's like to work at the edge of the unknown, where billion-dollar machines produce results that nobody fully understands. Picture this. You're a physicist who's dedicated your entire career to understanding antimatter. You've spent years learning the mathematics, mastering the experimental techniques, and developing an intuition for how these exotic particles should behave. Then you walk into the lab one morning, check the data from overnight experiments, and discover something that doesn't make sense according to everything you thought you knew. That's exactly what happened to the researchers working on the Lambda B baryon experiments. They weren't expecting to find such clear evidence of CP violation. The theoretical predictions suggested it might be there, but actually seeing it in the data was something else entirely. It's like knowing there might be treasure buried in your backyard and then actually striking gold with your shovel. But here's what makes the scientific process so fascinating. Finding something unexpected doesn't lead to celebration and champagne. It leads to months of double-checking, triple-checking, and peer review. Because in physics, being wrong is expensive. Not just financially, though. These experiments cost enormous amounts of money. Being wrong means potentially sending the entire field down the wrong path for years or decades. So when the LHCb team announced their CP violation discovery, they'd already spent countless hours making sure their result was solid. They'd checked their equipment, verified their analysis methods, and ruled out every possible source of error they could think of. They'd reached that magical threshold of 5.2 sigma statistical significance, meaning the probability of their result being a fluke was less than 1 in several million. But even with that level of confidence, the discovery raised more questions than it answered. Because while CP violation in baryons is exactly the kind of thing physicists have been looking for, the magnitude they measured still isn't large enough to explain the cosmic matter-antimatter imbalance. It's like finding a piece of the puzzle that clearly belongs somewhere, but you're not sure exactly where it fits in the bigger picture. This is where the real challenge of modern physics becomes apparent. The universe doesn't reveal its secrets through dramatic, obvious phenomena that anyone can observe. Instead, it whispers hints through tiny statistical deviations that require enormous machines and years of data collection to detect. And even when you do detect something, interpreting what it means requires connecting dots across multiple experiments, theoretical frameworks, and decades of accumulated knowledge. Consider the antimatter transport experiment. Moving antiprotons across the CERN campus might sound like a straightforward engineering challenge, but it represents years of development and testing. The mobile trap had to maintain a perfect vacuum while travelling over real roads with bumps, vibrations, and temperature changes. The magnetic containment system had to remain stable despite the Earth's magnetic field fluctuations and interference from nearby electrical equipment. The fact that it worked at all is remarkable. The fact that it worked well enough to keep antiproton stable for over 12 hours opens up research possibilities that didn't exist before, but it also demonstrates something important about how scientific progress actually happens. It's not usually a single dramatic breakthrough that changes everything overnight. Instead, it's the accumulation of hundreds of small advances that eventually enable something revolutionary. The same pattern emerges when you look at the gravity experiments with antihydrogen. Creating antihydrogen atoms and dropping them to test their gravitational response sounds simple enough, but the technical challenges are staggering. These atoms exist for only brief moments before annihilating with regular matter. They have to be created, trapped, cooled to nearly absolute zero, and then released under conditions so carefully controlled that the slightest disturbance would ruin the measurement. The alpha G and G bar experiments represent the culmination of decades of work on magnetic trapping, laser cooling, and precision measurement techniques. The fact that they can detect gravitational acceleration over distances of just a few centimeters using particles that barely exist long enough to fall showcases the incredible sophistication of modern experimental physics. But what's equally remarkable is what these experiments reveal about the scientific mindset. Researchers spent years developing the technology to answer a question that might seem almost philosophical. Does antimatter fall up or down? Most physicists expected it to fall down, just like regular matter. But nobody knew for certain, and in science, expectations aren't enough. You have to actually measure things. And when they finally made those measurements, the results confirmed theoretical expectations. Antimatter falls down, but buried in the data were tiny hints that something might be slightly different. Not dramatically different, not enough to overturn general relativity, but just different enough to make scientists look more carefully at their numbers. This is where the real art of experimental physics comes into play. How do you distinguish between genuine new physics and experimental uncertainty? How do you know when a small deviation from theoretical predictions represents a genuine discovery versus just the limitations of your measurement apparatus? How do you decide whether to pursue these hints or focus your limited resources on other research directions? These aren't just technical questions, they're strategic decisions that can determine the direction of an entire field for years to come. And they're being made by human beings who are just as susceptible to excitement, disappointment, and confirmation bias as anyone else. The difference is that the scientific process has built-in safeguards designed to catch and correct these human tendencies. Peer review, replication, statistical analysis, and open data sharing all serve to filter out mistakes and false positives. But they also slow down the pace of discovery, sometimes frustratingly so. When you think you might have found something important, waiting months or years for confirmation can feel like an eternity. That's the situation CERN researchers find themselves in right now. They've made several intriguing discoveries that might be pointing toward new physics, but none of them are quite definitive enough to claim a breakthrough. The CP violation in lambda B baryons is real, but not large enough to solve the cosmic mystery. The antimatter transport experiment worked, but hasn't yet led to new physics discoveries. The gravity measurements show antimatter behaving mostly as expected, but with tantalizing hints that something might be subtly different. It's like being a detective who's found several clues that seem related to the same case, but hasn't yet figured out how they all fit together. Each piece of evidence is interesting on its own, but the bigger picture remains frustratingly elusive. This uncertainty extends to the theoretical side of physics as well. While experimentalists are collecting data and making measurements, theorists are working to develop new models that might explain these observations. But theoretical physics has its own challenges and limitations. The standard model of particle physics has been incredibly successful at predicting experimental results for decades. It's one of the most thoroughly tested theories in the history of science. But it also has known limitations and gaps. It doesn't explain dark matter or dark energy. It doesn't explain why there are exactly 3 generations of fundamental particles. And it doesn't explain the matter-antimatter asymmetry that allows the universe to exist. Developing theories that go beyond the standard model requires walking a tightrope between innovation and constraint. New theories have to explain all the experimental results that the standard model already explains successfully, while also predicting new phenomena that haven't been observed yet. They have to be mathematically consistent, physically reasonable, and testable through experiments that are actually feasible with current or near-future technology. This is an enormously challenging task. There are literally thousands of theoretical papers published every year proposing various extensions to the standard model. Most of them will turn out to be wrong, but that's part of the process. Science advances through a combination of creative speculation and ruthless empirical testing. The antimatter mysteries at CERN represent a perfect example of this dynamic interplay between theory and experiment. Theorists have proposed dozens of mechanisms that might explain CP violation in baryons, antimatter transport phenomena, and gravitational interactions. Experimentalists are working to test these predictions and discover new phenomena that might support or refute different theoretical approaches. But this process takes time, often much more time than anyone involved would prefer. The LHC has been operating for over a decade, and while it's made numerous important discoveries, it hasn't yet found the clear evidence of new physics that many researchers hoped for. The antimatter experiments have achieved remarkable technical milestones, but they haven't yet solved the fundamental mysteries they were designed to investigate. This might sound discouraging, but it's actually how science normally works. Most research doesn't lead to dramatic breakthroughs. Instead, it gradually builds up our understanding through incremental advances, technical improvements, and the slow accumulation of more precise data. Occasionally, this process leads to genuine revolutions in our understanding, but those moments are rare and usually build on years or decades of preparatory work. The current situation at CERN might be setting the stage for exactly that kind of revolutionary moment. The combination of improved experimental techniques, more sophisticated theoretical models, and accumulating hints of new phenomena could be preparing the ground for a major breakthrough in our understanding of antimatter and the fundamental structure of reality. But it's also possible that the current mysteries will remain unsolved for years or decades to come. The universe doesn't reveal its secrets according to human timelines or research funding cycles. Some questions might require entirely new experimental approaches or theoretical insights that haven't been developed yet. What's certain is that the research will continue. The technical capabilities for studying antimatter keep improving year by year. New experimental techniques are being developed that can measure ever smaller effects with greater precision. International collaborations are sharing resources and expertise to tackle problems that no single institution could solve alone. The Puma experiment represents just one example of this continuing evolution. By combining antimatter physics with nuclear physics, researchers are exploring entirely new experimental territory. They're looking for clues in places where previous generations of scientists never thought to search. Other future experiments are being planned that will push the boundaries even further. Some involve studying antimatter in space, where Earth's magnetic field won't interfere with measurements. Others involve creating antimatter atoms with different compositions, or studying antimatter under extreme conditions of temperature and pressure. The technical challenges involved in these experiments are staggering, but so are the potential rewards. If researchers can solve the antimatter mystery, they won't just answer one specific question about particle physics. They'll potentially unlock new understanding of how the universe works at its most fundamental level. That understanding could have practical implications that we can't even imagine yet. Many of the most important technological advances in human history emerged from basic research that seemed purely academic at the time. Quantum mechanics led to computers and lasers. Relativity enabled GPS satellites. Nuclear physics led to both power generation and medical imaging. It's impossible to predict what practical applications might emerge from a deeper understanding of antimatter, but history suggests they could be transformative. More immediately, solving these mysteries would represent a triumph of human curiosity and ingenuity. It would demonstrate our species' ability to understand phenomena that are completely outside our everyday experience. The antimatter research at CERN represents humanity at its best. Thousands of scientists from dozens of countries working together to answer fundamental questions about the nature of reality. They're using the most sophisticated tools ever created to study phenomena that exist for fractions of a second under conditions that don't occur anywhere else in the solar system. And they're doing it not because it's easy or profitable, but because understanding the universe is one of the most deeply human impulses we have. The same curiosity that led our ancestors to wonder about the stars has evolved into experiments that can trap antimatter and measure its response to gravity with incredible precision. But perhaps most remarkably, they're doing it with an honesty and humility that's often missing from other human endeavors. When the data doesn't match expectations, scientists don't try to hide or rationalize the discrepancy. They double-check their work, share their methods with competitors, and admit when they don't understand something. This intellectual honesty is what makes scientific progress possible, even when that progress is slower and more uncertain than anyone would prefer. It's also what makes the current antimatter mysteries so compelling. We're watching the scientific process work in real time as researchers grapple with observations that don't quite fit existing theories. The story of antimatter at CERN isn't just about exotic particles and billion-dollar experiments. It's about the human quest to understand our place in the universe. It's about the determination to keep asking questions, even when the answers seem impossibly elusive. And it's about the faith that the universe, however strange and complex it might be, is ultimately comprehensible to creatures like us, who are themselves made of the matter whose existence remains such a profound mystery. Every measurement, every experiment, every tiny step forward in understanding brings us closer to answering questions that go to the very heart of existence itself. Why is there something rather than nothing? How did the universe come to be the way it is? What determines the fundamental laws that govern everything from subatomic particles to galaxies? These questions have fascinated humans for millennia, but only now do we have the tools to begin answering them through direct observation and measurement. The antimatter research at CERN represents one of our best opportunities to make progress on these deepest of mysteries. And regardless of what the ultimate answers turn out to be, the journey of discovery itself has already taught us something profound about the nature of reality and our ability to understand it. We live in a universe that's far stranger and more complex than our ancestors could have imagined, but it's also a universe that yields its secrets to careful observation, creative thinking, and persistent effort. The weird things happening with antimatter at CERN might eventually lead to a complete revolution in physics, or they might turn out to be subtle effects that don't fundamentally change our understanding of how the universe works. Either way, the research itself represents something remarkable about human nature and our relationship with the cosmos we inhabit. We're the products of a universe that shouldn't exist, using our minds to study the very mystery of our own existence. And somehow, against all odds, we're actually making progress. The scientists working on these cutting-edge antimatter experiments aren't just dealing with technical challenges. They're confronting something much more fundamental: the uncomfortable possibility that everything we thought we understood about the universe might be incomplete. Take the researchers studying CP violation in those lambda B baryons. They didn't wake up one morning expecting to find evidence that could shake the foundations of physics. They were running routine measurements, checking data that most people would find mind-numbingly boring. Columns of numbers, statistical analyses, calibration checks. The kind of work that requires incredible patience and attention to detail. But buried in those numbers was something that shouldn't have been there: a tiny asymmetry between how matter and antimatter particles behave during their brief existence, just 2.5%. In everyday life, that's nothing. The difference between a coffee cup that's 97.5% full and one that's completely full. But in particle physics, where symmetries are supposed to be absolute, that small difference might as well be a neon sign flashing, "Something is broken here." The statistical significance they achieved, 5.2 sigma, represents months of double-checking, triple-checking, and running the same analysis in different ways to make sure they weren't fooling themselves. Because in science, being wrong isn't just embarrassing. It can derail entire research programs and waste years of other people's work. But here's what makes this discovery so frustrating for physicists. It's real, it's significant, and it's still not enough. That 2.5% asymmetry, while groundbreaking in terms of detection, falls far short of explaining why the universe contains any matter at all. It's like finding a smoking gun that's only fired blanks. This pattern repeats across every antimatter experiment at CERN. Each discovery reveals something new and unexpected, but none of them provides the complete answer everyone is searching for. The mobile antimatter transport worked flawlessly, opening up possibilities for experiments that were previously impossible. But those future experiments haven't happened yet, and there's no guarantee they'll solve anything fundamental. The gravity experiments showed that antimatter falls down, just like regular matter, confirming what most physicists expected. But those tiny hints in the data, the measurements that were just slightly off from perfect predictions, keep nagging at researchers. Are they seeing genuine new physics, or just the limitations of their equipment? Without more precise measurements, it's impossible to know for certain. This uncertainty creates a strange psychological pressure for scientists working in the field. They're dealing with phenomena so rare and exotic that generating enough data to draw firm conclusions can take years or decades. Every measurement represents months of preparation, careful calibration, and analysis. And at the end of all that work, the most honest answer to fundamental questions is often, "We still don't know." That kind of uncertainty would be unbearable in most professions. Imagine being a doctor who could only give patients vague probabilities instead of definitive diagnoses, or an engineer whose bridges might or might not support the weight they're designed for. But in fundamental physics, uncertainty isn't a bug in the system, it's a feature. The universe doesn't owe us explanations that fit neatly into human timescales or budgets. Some questions might require entirely new, experimental approaches that haven't been invented yet. Others might demand theoretical insights that no one has thought of. And some might remain mysteries for generations to come. This reality shapes how physicists approach their work at CERN. They're not just conducting experiments, they're building the foundation for discoveries that might not happen for decades. The techniques they develop, the technologies they create, and the data they collect will be used by future scientists to answer questions that current researchers can't even formulate properly. Consider the anti-proton decelerator and ALINA systems that produce and slow down antimatter. These machines took years to design and build, and they've been operating for over a decade. Most of the antimatter they've produced has been used for basic studies that didn't lead to revolutionary discoveries. But each experiment taught researchers something new about how to handle these exotic particles more effectively. That accumulated knowledge made possible the recent transport experiment that moved antiprotons across the CERN campus. The transport experiment, in turn, will enable future studies that couldn't be conducted before. And those future studies might finally provide the insights that crack open the antimatter mystery. This incremental approach to discovery reflects something deeper about how science actually works versus how it's often portrayed in popular media. Real scientific breakthroughs rarely happen through sudden flashes of inspiration or dramatic eureka moments. Instead, they emerge from the slow accumulation of evidence, technique, and understanding. The scientists working on Puma, the upcoming experiment that will fire antimatter at unstable atomic nuclei, are building on decades of previous work. They're combining expertise from antimatter physics, nuclear physics, and precision engineering. The experiment they're planning would have been impossible just 10 years ago, not because the basic physics wasn't understood, but because the necessary technologies didn't exist. Every component of Puma represents the solution to problems that previous generations of physicists couldn't solve. The mobile antimatter trap builds on lessons learned from stationary containment systems. The methods for creating and studying unstable nuclei have been refined through years of practice. The precision measurement techniques have been borrowed from other fields and adapted for this specific application. Even if Puma succeeds beyond all expectations and reveals clear evidence of new physics, that discovery will itself raise new questions that require even more sophisticated experiments to answer. This is the nature of scientific progress. Each answer opens up new avenues of investigation that weren't visible before. But there's something uniquely challenging about antimatter research that sets it apart from other areas of physics. The particles being studied exist for incredibly brief periods under extremely artificial conditions. Unlike astronomy, where researchers can observe the same stars and galaxies night after night, antimatter experiments often involve phenomena that last for microseconds or less. This creates a strange relationship between the experimenters and their subject matter. They're studying the fundamental building blocks of reality, but they can only access those building blocks through machines that cost billions of dollars and require international cooperation to operate. The antimatter they create and study has no natural counterpart anywhere in the observable universe. In a sense, antimatter research represents the ultimate expression of human technological ambition. We're using the most sophisticated tools our species has ever created to study phenomena that don't exist in nature. We're asking questions about the fundamental structure of reality that can only be answered through experiments that push the boundaries of what's technically possible. The irony is that all this technological sophistication is being used to understand something that happened in the first moments after the Big Bang, when the universe was far simpler than it is today. The complex particle accelerators, magnetic traps, and precision measurement systems at CERN are all focused on recreating and studying conditions that existed naturally when the cosmos was less than a second old. This temporal disconnect adds another layer of abstraction to antimatter research. Scientists aren't just studying exotic particles, they're trying to understand cosmic history through laboratory experiments. They're using present-day technology to investigate past events that determine the future evolution of everything that exists. The success of this approach depends on something that's not guaranteed, the assumption that the same physical laws that operate in CERN's experiments also operated in the early universe. This assumption is probably correct, but it's still an assumption. The conditions during the first moments after the Big Bang were so extreme that they can't be fully replicated in any laboratory. Temperature, pressure, energy density, and the rate of cosmic expansion during those early moments were all far beyond anything that can be achieved on Earth. Scientists can create tiny regions of space where individual particles have similar energies to those that existed in the early universe, but the overall environment is completely different. This limitation doesn't invalidate antimatter research, but it does add an element of uncertainty to interpreting the results. When CERN experiments reveal subtle differences between matter and antimatter behavior, scientists have to ask whether those same differences would have been significant under early universe conditions. The mathematical models that connect laboratory measurements to cosmic evolution involve numerous assumptions and approximations. Small changes in those assumptions can lead to dramatically different conclusions about what happened during the first moments after the Big Bang. This is where theoretical physics becomes crucial to understanding antimatter research. Experimentalists can measure what happens in their detectors, but they need theorists to help interpret what those measurements mean for our understanding of the universe as a whole. The relationship between theory and experiment in particle physics is complex and sometimes tense. Theorists develop mathematical models that make predictions about what should happen in experiments. Experimentalists design tests to check whether those predictions are correct. When the experiments disagree with theory, both sides have to figure out whether the problem lies with the theoretical model, the experimental measurement, or both. In the case of antimatter research, this process is complicated by the fact that many theoretical predictions are extremely difficult to test directly. The differences between matter and antimatter behavior that could explain cosmic evolution might be far too small to detect with current experimental techniques. This creates a frustrating situation where theorists can propose elegant solutions to the antimatter mystery, but experimentalists can't definitively prove or disprove those solutions. The best they can do is set limits on how large certain effects can be, gradually constraining the range of possible theoretical explanations. The CP violation discovered in lambda B baryons illustrates this dynamic perfectly. Theorists had predicted that this type of violation should exist, but they couldn't predict exactly how large it would be. The experimental measurement confirmed that the violation is real, but it also showed that it's probably too small to explain the cosmic matter-antimatter imbalance by itself. This doesn't mean the theoretical predictions were wrong. It means they were incomplete. There might be other sources of CP violation that haven't been discovered yet, or there might be entirely different mechanisms that contribute to the cosmic asymmetry. The experimental result provides one piece of the puzzle, but the complete picture remains unclear. This interplay between theory and experiment will continue to drive antimatter research for years to come. As experimental techniques improve and new measurements become possible, theorists will refine their models and develop new predictions. As theoretical understanding advances, experimentalists will design new tests to probe previously unexplored aspects of antimatter behavior. The Puma experiment represents one example of this ongoing evolution. The basic idea of using antimatter to probe nuclear structure has been around for decades, but only recently have the experimental techniques advanced enough to make it feasible. The theoretical framework for interpreting the results is still being developed, but the potential for new discoveries is enormous. Future antimatter experiments will likely push this envelope even further. Space-based studies could eliminate many of the environmental interferences that complicate ground-based measurements. More powerful accelerators could create antimatter with different properties or in larger quantities. New detection technologies might reveal subtle effects that current instruments can't measure. But perhaps the most important developments will be conceptual rather than technological. The current generation of antimatter researchers is learning to think about these problems in new ways, questioning assumptions that previous generations took for granted. The idea that matter and antimatter should behave as perfect opposites, for example, is being challenged by the accumulating evidence of subtle asymmetries. The assumption that gravitational effects on antimatter should be identical to those on regular matter is being tested directly for the first time. The notion that antimatter research should focus only on fundamental particles is being expanded to include studies of how antimatter interacts with complex nuclear systems. These conceptual shifts might ultimately prove more important than any specific experimental result. Science advances not just through the accumulation of data, but through changes in how researchers think about problems. New ways of asking questions can reveal possibilities that weren't apparent before. The weird things happening with antimatter at CERN might be pointing toward exactly this kind of conceptual revolution. The discoveries being made don't fit neatly into existing theoretical frameworks, but they're not dramatic enough to immediately overturn those frameworks either. This ambiguous situation forces scientists to grapple with fundamental questions about the nature of scientific knowledge itself. How do you decide when accumulating anomalies justify abandoning a successful theory in favor of something completely new? How do you distinguish between genuine new physics and experimental artifacts? How do you maintain scientific rigor while remaining open to revolutionary possibilities? These questions don't have easy answers, but they're central to how science progresses. The history of physics is filled with examples of discoveries that seemed insignificant at first but eventually led to major revolutions in understanding. It's also filled with examples of apparent anomalies that turned out to be experimental mistakes or misinterpretations. The current antimatter mysteries at CERN could fall into either category. They might be the first signs of a coming revolution in our understanding of fundamental physics, or they might be subtle effects that don't fundamentally change the big picture. The only way to find out is to keep doing experiments, collecting data, and refining theoretical models. What's certain is that this process will continue regardless of what the ultimate answers turn out to be. The questions that drive antimatter research touch on some of the deepest mysteries of existence. Why does the universe exist at all? What determines the fundamental laws of physics? Are there aspects of reality that we haven't even imagined yet? These questions have fascinated humans for thousands of years, but only recently have we developed the tools to begin answering them through direct observation and measurement. The antimatter research at CERN represents one of our best opportunities to make progress on these ultimate mysteries. But the research also represents something more immediate and practical. It's training a new generation of scientists in techniques and ways of thinking that will be valuable regardless of what specific discoveries they make. The students and postdocs working on antimatter experiments today are learning to handle problems of extraordinary technical complexity and conceptual subtlety. They're developing skills in precision measurement, statistical analysis, international collaboration, and scientific communication that will serve them throughout their careers. Many of them will eventually move on to other fields, taking with them the problem-solving approaches they learned while studying antimatter. This human dimension of the research is often overlooked, but it's crucial to the long-term impact of programs like those at CERN. Scientific institutions don't just produce discoveries, they produce scientists. And the scientists they produce carry forward not just specific knowledge, but ways of thinking about problems that can be applied to challenges we haven't even identified yet. The antimatter mystery might remain unsolved for decades, but the process of trying to solve it is already generating benefits that extend far beyond particle physics. Technologies developed for antimatter research find applications in medical imaging, materials science, and computing. Theoretical insights from particle physics influence our understanding of condensed matter systems, cosmology, and even biology. More fundamentally, the antimatter research at CERN exemplifies humanity's capacity for curiosity-driven investigation. In a world increasingly focused on short-term practical problems, this kind of basic research represents a commitment to understanding for its own sake. That commitment has historically proven to be one of our species' most valuable investments. Most of the technologies that define modern civilization emerged from basic research that seemed completely impractical when it was first conducted. The transistors in our computers, the lasers in our communication systems, and the magnetic resonance imaging machines in our hospitals all trace their origins back to abstract investigations of fundamental physics. The weird things happening with antimatter at CERN might someday lead to equally transformative applications, or they might remain purely academic curiosities. Either way, the research itself represents something important about human nature and our relationship with the universe we inhabit. We're a species that emerged from cosmic evolution, using our evolved brains to study the very processes that brought us into existence. We're asking questions about the fundamental nature of reality, using tools and concepts that are themselves products of that reality, and somehow, against all odds, we're making progress. The antimatter mystery at CERN embodies both the promise and the challenge of this extraordinary endeavour. We're close enough to fundamental answers to taste them, but still far enough away that they remain tantalizingly out of reach. We have the tools to study phenomena that our ancestors couldn't even imagine, but we're still limited by the same human cognitive capabilities that evolved to help us survive in a very different environment. This tension between our technological capabilities and our conceptual limitations shapes every aspect of modern physics research. We can build machines that recreate conditions from the first moments after the Big Bang, but we still struggle to understand what those conditions mean for the nature of reality itself. The scientists working at CERN are navigating this tension every day. They're using the most sophisticated instruments ever created to probe questions that might not have definitive answers. They're collaborating across cultural and linguistic barriers to tackle problems that no individual or single institution could solve alone. And they're doing it all while knowing that most of their experiments will probably not lead to revolutionary discoveries. This takes a particular kind of courage and commitment that's often underappreciated. It's easy to stay motivated when you're confident that your work will lead to clear success. It's much harder to maintain enthusiasm when you're exploring territory where success isn't guaranteed and might not be recognizable, even if it occurs. The antimatter researchers at CERN are essentially explorers venturing into uncharted intellectual territory. They don't know what they'll find, or even whether there's anything significant to be found. But they keep going because the questions they're asking are too important to abandon, and because the process of exploration itself has value regardless of what specific discoveries it produces. This exploration is far from over. The weird things happening with antimatter at CERN are just the beginning of what promises to be a long and complex investigation. New experiments are being planned that will push the boundaries of what's technically possible. New theoretical frameworks are being developed that might finally make sense of the accumulating puzzles. And new generations of scientists are being trained who will carry this work forward long after the current researchers have moved on. The antimatter mystery spans multiple human lifetimes, and solving it will require sustained effort across decades or centuries. But that's not a reason for discouragement. It's a reason for excitement. We're participating in one of the greatest intellectual adventures in human history. We're trying to understand the deepest secrets of the universe using the most powerful tools our species has ever created. And we're making progress, even if that progress is slower and more uncertain than we might prefer. The story of antimatter at CERN is ultimately a story about human curiosity and determination. It's about our refusal to accept mystery as the final answer to fundamental questions. It's about our willingness to invest enormous resources and effort in understanding things that have no immediate practical application. And it's about our faith that the universe, however strange and complex it might be, is ultimately comprehensible to creatures like us who are themselves products of cosmic evolution. That faith might be misplaced, but it's driven every major advance in human understanding of the natural world. The weird things happening with antimatter at CERN might vindicate that faith in spectacular fashion, or they might reveal that some questions are beyond our current capacity to answer. Either way, the investigation itself represents something remarkable about what it means to be human in a universe that continues to surprise us at every turn. The questions driving this research extend beyond just antimatter itself. They're forcing scientists to reconsider fundamental assumptions about how the universe operates at its most basic level. Because if tiny violations in symmetry can accumulate over cosmic time, then maybe the rules governing reality are more flexible than anyone imagined. Think about what this means for a moment. Every equation in physics textbooks assumes certain symmetries hold absolutely. The idea that flipping matter to antimatter and reversing spatial coordinates should leave physical laws unchanged isn't just a mathematical convenience. It's supposed to be a fundamental truth about how reality works. But if that truth has exceptions, even tiny ones, then everything built on top of it becomes questionable. This is why the recent discoveries at CERN are creating such a stir in the physics community. It's not just about finding new particles or confirming existing theories. It's about discovering that the universe might be playing by slightly different rules than we thought. Rules that are subtle enough to hide for billions of years, but significant enough to determine whether anything exists at all. The implications ripple outward, from particle physics into cosmology, quantum mechanics, and even our understanding of time itself. If matter and antimatter don't behave as perfect mirrors of each other, what does that say about other fundamental symmetries? Are there violations in time reversal symmetry? In the relationship between left and right-handedness in particle interactions? How many other supposedly ironclad rules of physics might have tiny loopholes that become significant under extreme conditions? These questions are driving the next wave of experiments at CERN and laboratories around the world. Researchers are designing tests to probe symmetries that have never been questioned before. They're looking for violations so small that detecting them requires pushing measurement precision to its absolute limits. But there's another dimension to this mystery that's equally fascinating. The violations they're finding aren't random or chaotic. They follow specific patterns that seem to be built into the fabric of reality itself. It's as if the universe has a subtle preference for matter over antimatter that's coded into its fundamental operating system. This preference is incredibly weak. We're talking about effects that are typically measured in percentages of percentages. But weakness doesn't mean insignificance when you're dealing with cosmic scales and billions of years of evolution. A tiny bias, compounded over the entire history of the universe, can lead to dramatic consequences. The math is actually quite elegant when you work it out. Starts with equal amounts of matter and antimatter in the early universe. Add a tiny violation that favors matter by just 1 part in 10 billion. Let the annihilation process run for a few microseconds after the Big Bang. What you end up with is exactly the kind of matter-dominated universe we observe today. But here's where things get really interesting. The violations scientists are measuring at CERN still aren't quite large enough to explain this cosmic preference completely. They're close, tantalizingly close, but not quite sufficient. This suggests there might be additional sources of asymmetry that haven't been discovered yet. Maybe there are other types of particles that exhibit stronger violations. Maybe there are interactions between different symmetry-breaking mechanisms that amplify small effects into larger ones. Maybe the conditions in the early universe were different enough from laboratory conditions that the same physical processes produce different outcomes. Or maybe the explanation lies in something completely unexpected. Physics has a long history of surprises, where the answer to one mystery reveals entirely new layers of complexity that nobody anticipated. The discovery that neutrinos have mass, for example, opened up whole new areas of research that are still being explored decades later. The antimatter mystery might be heading in a similar direction. Each new measurement reveals additional puzzles that require even more sophisticated experiments to investigate. The mobile antimatter transport system that worked so successfully is already being used to plan studies that would have been impossible just a few years ago. Scientists are designing experiments to test antimatter behavior under different gravitational conditions, perhaps by taking it to higher altitudes where Earth's gravity is slightly weaker. They're planning to study how antimatter responds to magnetic fields of different strengths and orientations. They're even investigating whether antimatter might interact differently with the various fields that permeate empty space. These studies are pushing the boundaries of what's technically feasible with current technology. Keeping antimatter stable during transport was challenging enough when it involved a carefully planned route across the CERN campus. Maintaining stability during airplane flights or rocket launches presents entirely new sets of engineering problems. But the potential scientific payoff is enormous. If antimatter behaves even slightly differently under different environmental conditions, that could provide crucial clues about why it's so rare in the natural universe. Maybe antimatter is more sensitive to cosmic background radiation than regular matter. Maybe it interacts differently with dark matter or dark energy. Maybe it responds to gravitational waves in ways that regular matter doesn't. These possibilities might sound like science fiction, but they're being seriously investigated by researchers who understand that the universe has already surprised us in ways that seemed impossible just a few decades ago. The discovery of dark energy, which makes up most of the universe's content, came as a complete shock to the cosmology community. The detection of gravitational waves required technological capabilities that didn't exist when Einstein first predicted their existence. The antimatter research at CERN is operating in this same spirit of exploration into the unknown. Researchers are following experimental evidence wherever it leads, even when it points toward conclusions that challenge fundamental assumptions about how physics works. This approach has already led to some unexpected discoveries that extend beyond antimatter itself. The precision measurement techniques developed for studying particle symmetries have revealed new insights into the behavior of ordinary matter under extreme conditions. The magnetic containment systems designed for antimatter traps have applications in fusion energy research and plasma physics. The international collaboration required for these experiments has created new models for scientific cooperation that are being applied to other large-scale research projects. The data analysis methods developed to extract tiny signals from enormous datasets have found applications in fields ranging from medical imaging to climate science. But perhaps the most significant impact is conceptual rather than technological. The antimatter research is forcing scientists to think more carefully about the relationship between symmetry and reality. For most of the 20th century, physicists assumed that fundamental symmetries were exact and universal. The discovery of symmetry violations has revealed that reality is more nuanced and complex than those simple assumptions suggested. This shift in perspective is influencing research across multiple areas of physics. Particle theorists are developing new models that incorporate symmetry breaking as a fundamental feature rather than an exotic exception. Cosmologists are investigating how symmetry violations in the early universe might have influenced the formation of galaxies and large-scale structure. Even areas that seem completely unrelated to antimatter research are benefiting from these new ways of thinking about symmetry and asymmetry. Condensed matter physicists studying superconductors and other exotic materials are finding that subtle symmetry breaking effects can lead to dramatic changes in material properties. The ripple effects extend into technology development as well. Understanding how tiny asymmetries can accumulate into large-scale effects is relevant to everything from computer chip manufacturing to pharmaceutical design. The precision measurement techniques pioneered in antimatter research are finding applications in fields that require detecting incredibly small signals against noisy backgrounds. But for all these practical benefits, the core mystery remains unsolved. Why does the universe prefer matter over antimatter? The question that drove the construction of billion-dollar particle accelerators and the development of antimatter containment technology is still waiting for a complete answer. The recent discoveries at CERN have provided important clues, but they've also revealed that the full explanation is likely to be more complex than anyone anticipated. The CP violation in lambda B baryons is real and significant, but it's not sufficient by itself. The successful transport of antimatter opens up new experimental possibilities, but those possibilities haven't been fully explored yet. The gravity experiments have confirmed that antimatter responds to gravitational forces much like regular matter, but the tiny hints of difference in the data suggest there might be subtle effects that haven't been fully characterized. Each answer seems to generate new questions that require even more sophisticated experiments to address. This pattern of discovery leading to deeper mystery is actually quite common in fundamental physics research. The more precisely scientists can measure natural phenomena, the more subtle effects they uncover that weren't visible with less sensitive instruments. What initially appears to be a simple question often turns out to involve multiple layers of complexity that take decades to unravel. The antimatter mystery is following exactly this trajectory. The basic question of why matter dominates over antimatter seemed straightforward when it was first formulated. Find the mechanism that creates asymmetry between matter and antimatter, measure its strength, and verify that it's sufficient to explain cosmic evolution. Simple in principle, extraordinarily difficult in practice. The reality has turned out to be far more complex. There appear to be multiple mechanisms that contribute to matter-antimatter asymmetry, each operating under different conditions and with different strengths. Some effects are large enough to measure directly with current technology. Others might be too small to detect with any foreseeable experimental setup. Some asymmetries might only become significant under the extreme conditions that existed in the early universe. Others might require interactions between particles and fields that don't occur naturally in the current cosmos. Sorting out which effects are important and how they combine to produce the observed matter dominance is a challenge that will likely occupy researchers for many years to come. But this complexity isn't a cause for despair. It's a sign that the universe is richer and more interesting than simplified theoretical models suggested. Each new layer of complexity that gets uncovered reveals new opportunities for discovery and understanding. The fact that reality refuses to fit into neat theoretical boxes is what keeps science exciting and unpredictable. The researchers working on antimatter at CERN understand this dynamic very well. They're not expecting to solve cosmic mysteries with a single decisive experiment. Instead, they're building up a comprehensive picture through multiple complementary approaches, each contributing pieces to a puzzle that's larger and more intricate than anyone initially imagined. The Puma experiment, which will fire antimatter at unstable atomic nuclei, represents one piece of this larger puzzle. By studying how antiprotons interact with exotic nuclear systems, researchers hope to learn more about the fundamental forces that operate inside atomic nuclei. This information might reveal new sources of asymmetry that haven't been considered before, but Puma is just one of many experiments being planned or conducted. Other research groups are investigating antimatter behavior under different conditions, using different types of particles and probing different aspects of fundamental symmetries. The combination of results from all these studies will eventually paint a more complete picture of how antimatter fits into the larger structure of physical reality. This collaborative approach to solving fundamental mysteries represents one of the great strengths of modern physics research. No single experiment or research group has all the answers, but by sharing data, techniques, and insights across the global scientific community, researchers can tackle problems that would be impossible for any individual institution to solve. The antimatter research at CERN exemplifies this collaborative spirit. Scientists from dozens of countries are working together, sharing not just the costs and technical challenges, but also the intellectual excitement of exploring the unknown. They're united by curiosity about fundamental questions that transcend national boundaries and cultural differences. This international cooperation isn't just practically necessary for conducting expensive experiments, it's also intellectually essential for making progress on problems that require multiple perspectives and approaches. Different research traditions and educational backgrounds bring different insights to complex problems. The diversity of viewpoints represented in large collaborative projects often leads to creative solutions that wouldn't emerge from more homogeneous research groups. The antimatter mystery is exactly the kind of problem that benefits from this diversity of approaches. It sits at the intersection of particle physics, cosmology, nuclear physics, and precision measurement science. Solving it requires expertise from all these areas, plus innovative thinking that combines insights from different fields in novel ways. The weird things happening with antimatter at CERN are just the beginning of what promises to be a long and fascinating investigation. As experimental techniques continue to improve and new theoretical insights emerge, researchers will undoubtedly uncover additional surprises that nobody can anticipate yet. Some of these surprises might finally provide the missing pieces needed to solve the matter-antimatter asymmetry puzzle. Others might reveal entirely new mysteries that require completely different experimental approaches to investigate. Either way, the research will continue to push the boundaries of human understanding about the fundamental nature of reality. The scientists working on these problems understand that they're participating in something much larger than any individual career or research project. They're contributing to humanity's ongoing effort to understand our place in the universe and the physical laws that govern everything from subatomic particles to galactic clusters. This perspective helps sustain motivation through the inevitable frustrations and setbacks that accompany any ambitious research program. Experiments fail, equipment breaks down, theoretical predictions turn out to be wrong, and promising results sometimes can't be reproduced. But the larger goal of understanding how the universe works provides a sense of purpose that transcends these temporary disappointments. The antimatter research at CERN embodies this long-term perspective on scientific discovery. The questions being investigated are so fundamental, and the technical challenges so demanding that progress necessarily occurs over timescales measured in decades rather than years. Individual researchers might spend their entire careers working on small pieces of the larger puzzle, knowing that the complete solution might not emerge until long after they've retired. But that's not a reason for discouragement. It's a testament to the importance and difficulty of the questions being asked. The fact that understanding antimatter requires such sustained effort and sophisticated technology demonstrates just how profound the mysteries are that researchers are attempting to solve. Every measurement, every successful experiment, and every theoretical insight contributes to a growing body of knowledge that future scientists will build upon. The current generation of antimatter researchers is laying the groundwork for discoveries that might not happen for many years, but that will ultimately transform our understanding of how the universe works. This intergenerational aspect of scientific research is often overlooked, but it's crucial to how major advances actually occur. Most scientific breakthroughs build on decades or centuries of preparatory work by researchers who never lived to see the final results of their efforts. The scientists working at CERN today are continuing this tradition, contributing to investigations that began long before they were born and will continue long after they're gone. The weird things happening with antimatter represent one chapter in this much larger story of human curiosity and scientific discovery. Whether the current mysteries get solved in the next few years or remain puzzling for decades to come, the research itself is already advancing our understanding of fundamental physics in ways that will have lasting value. And perhaps that's the most important point to remember about the antimatter research at CERN. The ultimate goal isn't just to solve specific puzzles about particle symmetries or cosmic evolution, it's to push the boundaries of human knowledge into territories that no previous generation could explore. It's to ask questions that our ancestors couldn't even formulate, and to seek answers using tools and concepts that represent the cutting edge of human technological and intellectual achievement. The weird things happening with antimatter at CERN are weird precisely because they're revealing aspects of reality that don't match our everyday intuitions or even our most sophisticated theoretical models. They're showing us that the universe is stranger and more complex than we imagined, but also that it's comprehensible to creatures like us who are determined enough to keep asking questions and clever enough to devise ways of answering them. That combination of strangeness and comprehensibility is what makes fundamental physics research so compelling. We're discovering that we live in a universe that consistently surprises us, but that also yields its secrets to careful observation and creative thinking. The antimatter mystery at CERN exemplifies both aspects of this relationship between human curiosity and cosmic reality. Whatever the ultimate answers turn out to be, the research itself has already changed how scientists think about the fundamental structure of reality. The idea that the universe might have built-in preferences, subtle biases that only become apparent under the most extreme conditions, represents a profound shift from the classical view of physics as a perfectly balanced system. This shift is influencing research far beyond antimatter studies. Cosmologists are investigating whether these tiny asymmetries might explain other puzzling features of the universe, like why dark matter seems to interact so weakly with ordinary matter, or why the expansion of space appears to be accelerating. Particle theorists are developing new mathematical frameworks that treat symmetry breaking as a fundamental feature of reality rather than an exotic exception. Even the experimental techniques being developed at CERN are finding unexpected applications. The magnetic containment systems designed for antimatter traps are being adapted for fusion energy research, where scientists need to confine extremely hot plasma without letting it touch any physical container. The precision measurement methods used to detect tiny particle asymmetries are being applied to gravitational wave detectors, where researchers need to measure changes in distance smaller than a fraction of a proton diameter. But perhaps the most significant impact is conceptual. The antimatter research is teaching scientists to look for effects that are almost impossibly small but potentially cosmic in their consequences. This perspective is changing how researchers approach other fundamental questions in physics. Consider the hierarchy problem, one of the deepest puzzles in particle physics. Why is gravity so much weaker than the other fundamental forces? The answer might involve symmetry-breaking mechanisms, similar to those that create matter-antimatter asymmetry. Tiny effects that seem negligible at the particle level might accumulate into the enormous differences in force strength that we observe. Or, take the measurement problem in quantum mechanics. Why do quantum superpositions collapse into definite states when observed? The answer might involve subtle asymmetries in how information flows through quantum systems. Effects too small to detect in individual measurements might become significant when billions of quantum events occur simultaneously. These connections between apparently unrelated problems illustrate why the antimatter research at CERN matters beyond its immediate goals. The experimental techniques, theoretical insights, and ways of thinking being developed to study antimatter are providing tools for investigating mysteries across all of physics. The researchers working on these problems understand that they're not just studying exotic particles, they're developing new approaches to understanding how the universe works at its most fundamental level. The precision required to detect antimatter asymmetries is pushing measurement science to its absolute limits. The theoretical frameworks needed to explain these asymmetries are revealing new mathematical structures that might apply to other areas of physics. This interdisciplinary impact is already becoming apparent in the design of future experiments. The next generation of gravitational wave detectors will incorporate measurement techniques pioneered in antimatter research. Future dark matter searches will use containment methods adapted from antimatter traps. Quantum computing researchers are studying how antimatter behaves in magnetic fields to develop better ways of controlling quantum information. But the influence flows in both directions. Advances in other fields are also contributing to antimatter research. Developments in quantum error correction are helping scientists maintain the stability of antimatter traps for longer periods. Progress in materials science is enabling the construction of more sensitive detectors that can measure smaller asymmetries. Improvements in computational methods are allowing theorists to model antimatter behavior with greater accuracy. This cross-pollination between different areas of research represents one of the great strengths of modern physics. Problems that seem completely unrelated often turn out to share underlying mathematical structures or experimental challenges. Solutions developed for one problem frequently find unexpected applications in completely different contexts. The antimatter mystery exemplifies this interconnectedness. What started as a specific question about particle symmetries has evolved into a research program that touches on cosmology, nuclear physics, quantum mechanics, and precision measurement science. The experimental techniques being developed to study antimatter are finding applications in fields ranging from medical imaging to quantum computing. This breadth of impact helps justify the enormous investment required for antimatter research. The Large Hadron Collider costs billions of dollars to operate, and the specialized equipment needed for antimatter experiments requires international collaboration to develop and maintain. But the returns on this investment extend far beyond the specific goals of any individual experiment. The technologies being developed at CERN have historically led to innovations that transform entire industries. The World Wide Web was invented at CERN to help physicists share data between different research institutions. Medical imaging techniques based on particle detection methods have revolutionized diagnostic medicine. Advanced materials developed for particle detectors have found applications in everything from solar panels to smartphone screens. The current antimatter research is likely to produce similar spin-offs, though it's impossible to predict exactly what form they'll take. The precision control systems needed to manipulate antimatter might lead to advances in nanotechnology or robotics. The data analysis methods used to extract tiny signals from enormous datasets might revolutionize artificial intelligence or financial modeling. But even if the antimatter research never produces any practical applications, it would still be valuable for its contribution to human understanding. The questions being investigated touch on the deepest mysteries of existence. Why does anything exist at all? What determines the fundamental laws that govern reality? Are there aspects of the universe so subtle that we're only just beginning to glimpse them? These questions have fascinated humans for millennia, but only recently have we developed the tools to begin answering them through direct observation and measurement. The antimatter research at CERN represents one of our best opportunities to make progress on these ultimate mysteries. The scientists working on these problems understand the historical significance of what they're attempting. They're participating in humanity's ongoing effort to understand our place in the universe and the physical laws that determine everything from the behavior of subatomic particles to the evolution of galaxies. This perspective helps sustain motivation through the inevitable challenges and setbacks that accompany any ambitious research program. Antimatter experiments are extraordinarily difficult to conduct. The particles being studied exist for incredibly brief periods under highly artificial conditions. Equipment failures can destroy months of preparation. Theoretical predictions often turn out to be incomplete or incorrect. But these difficulties are part of what makes the research so valuable. Easy questions have already been answered. The problems that remain unsolved are those that require pushing human knowledge and technology to their absolute limits. The antimatter mystery represents exactly this kind of ultimate challenge. Every successful measurement, every technological breakthrough, and every theoretical insight contributes to humanity's growing understanding of how the universe actually works. The current generation of researchers is building on work that began decades ago and laying the foundation for discoveries that might not happen for many years to come. This long-term perspective is essential for understanding the true significance of what's happening at CERN. Individual experiments might not provide complete answers to fundamental questions, but they're contributing pieces to a puzzle that's much larger than any single investigation. The weird things happening with antimatter represent just one aspect of this larger effort to understand the deepest workings of reality. Other experiments at CERN and laboratories around the world are investigating dark matter, extra dimensions, quantum gravity, and dozens of other mysteries that challenge our current understanding of physics. Each of these research programs is contributing to a gradually emerging picture of how the universe works at levels of detail and precision that previous generations couldn't imagine. The antimatter research is providing crucial pieces of this larger puzzle, revealing how the most fundamental symmetries of nature might not be as perfect as scientists once assumed. The implications of this discovery extend far beyond particle physics. If the basic symmetries that govern matter and antimatter can be violated, what does that say about other supposedly fundamental principles? Are there violations of time reversal symmetry that we haven't detected yet? Violations of the symmetry between left and right-handedness in particle interactions? How many other ironclad rules of physics might have subtle exceptions that become important under extreme conditions? These questions are driving the next wave of experiments at CERN and other research facilities. Scientists are designing tests to probe symmetries that have never been seriously questioned before. They're looking for violations so small that detecting them requires measurement precision that pushes technology to its absolute limits. But they're also developing new theoretical frameworks that can accommodate symmetry violations as natural features of the universe rather than exotic anomalies. These new theories are suggesting possibilities that seem almost too strange to believe, but that might be necessary to explain the full complexity of how reality actually works. Some theories propose that our universe is just one of many, each with slightly different physical laws determined by how symmetries were broken during cosmic inflation. Others suggest that the apparent violations we observe might be shadows of interactions with dimensions of space that we can't directly perceive. Still others propose that antimatter might interact with fields or forces that regular matter doesn't experience. These ideas might sound like science fiction, but they're being developed by serious scientists using rigorous mathematical methods. The antimatter research at CERN is providing the experimental tests needed to determine which of these speculative theories might actually describe reality. The process of testing such exotic theories requires experimental techniques that didn't exist just a few years ago. The ability to transport antimatter between buildings, for example, opens up possibilities for studying how these particles behave under different environmental conditions. Maybe antimatter responds differently to cosmic background radiation than regular matter. Maybe it interacts with Earth's magnetic field in ways that haven't been detected yet. The Puma experiment, which will fire antimatter at unstable atomic nuclei, represents another frontier in this exploration of the unknown. By studying how antiprotons interact with exotic nuclear systems, researchers hope to discover new sources of asymmetry that might help explain the cosmic matter-antimatter imbalance. But Puma also represents something more ambitious. It's an attempt to use antimatter as a tool for investigating other mysteries of nuclear physics. The debris produced when antiprotons annihilate with atomic nuclei contains information about nuclear structure that can't be obtained through any other experimental method. This approach of using one mystery to investigate another is becoming increasingly common in fundamental physics research. The tools and techniques developed to study antimatter are being applied to problems in cosmology, condensed matter physics, and quantum information science. Conversely, advances in these other fields are contributing new insights and methods to antimatter research. This cross-fertilization between different areas of physics is accelerating the pace of discovery in ways that wouldn't be possible if researchers worked in isolation. The antimatter mystery is benefiting from theoretical insights developed for cosmology, experimental techniques borrowed from atomic physics, and computational methods adapted from quantum mechanics. At the same time, the antimatter research is contributing to progress in all these other fields. The precision measurement techniques being developed at CERN are finding applications in gravitational wave detection and dark matter searches. The theoretical frameworks being developed to explain antimatter asymmetries are providing new approaches to understanding cosmic inflation and the formation of large-scale structure in the universe. This interconnectedness reflects something fundamental about how modern science works. The traditional boundaries between different fields of physics are becoming increasingly blurred as researchers recognize that apparently separate phenomena often share underlying connections. The antimatter mystery sits at the intersection of multiple disciplines, and solving it will require insights from all of them. The scientists working on these problems understand that they're not just investigating isolated questions about exotic particles. They're exploring the fundamental unity that underlies all of physics. The same mathematical structures that describe antimatter behavior also govern the evolution of galaxies, the behavior of quantum computers, and the dynamics of black holes. This unity isn't immediately obvious because different phenomena occur on vastly different scales of size, energy, and time. But the research being conducted at CERN is revealing deep connections between processes that seem completely unrelated. The tiny asymmetries that distinguish matter from antimatter might be related to the large-scale structure of space-time. The forces that confine quarks inside protons might be connected to the mechanisms that drive cosmic inflation. These connections are only beginning to be understood, but they're already changing how physicists think about the relationship between different areas of research. The antimatter mystery is providing a window into this deeper unity, revealing how phenomena that occur on the smallest possible scales can have consequences that shape the entire universe. The weird things happening with antimatter at CERN are weird precisely because they're showing us aspects of this unity that don't match our everyday intuitions. We're discovering that the universe operates according to principles that are far more subtle and complex than the simple mechanical models that dominated physics for centuries. But this complexity isn't random or chaotic. It follows mathematical patterns that are elegant and beautiful, even when they're difficult to understand. The symmetry violations that distinguish matter from antimatter, for example, follow precise rules that can be described using sophisticated mathematical frameworks developed over decades of theoretical research. These mathematical structures are revealing new aspects of how reality works at its most fundamental level. They're showing us that the universe is both stranger and more comprehensible than we imagined. Strange because the actual rules governing reality are far more complex than simple intuition suggests. Comprehensible because these complex rules can be understood and described using mathematical tools that human minds can master. This combination of strangeness and comprehensibility is what makes fundamental physics research so compelling. Every new discovery reveals that we live in a universe that consistently surprises us, but that also yields its secrets to careful observation and creative thinking. The antimatter mystery at CERN exemplifies both aspects of this relationship between human curiosity and cosmic reality. The research will continue regardless of how long it takes to find complete answers to the fundamental questions being investigated. Each measurement, each successful experiment, and each theoretical insight contributes to humanity's growing understanding of how the universe actually works. And that understanding, however incomplete it might be at any given moment, represents one of our species' greatest achievements. We're creatures that emerged from cosmic evolution, using our evolved brains to study the very processes that brought us into existence. We're asking questions about the fundamental nature of reality, using tools and concepts that are themselves products of that reality, and somehow against all odds, we're making progress toward answers that our ancestors couldn't even imagine. The antimatter mystery at CERN embodies both the promise and the challenge of this extraordinary endeavour. We're close enough to fundamental answers to sense their presence, but still far enough away that they remain tantalizingly out of reach. We have the tools to study phenomena that previous generations couldn't even conceive of, but we're still limited by the same human cognitive capabilities that evolved to help us survive in a very different environment. Navigating this tension between our technological capabilities and our conceptual limitations requires a particular kind of intellectual courage. The scientists working at CERN are venturing into territory where established theories might be incomplete and where experimental results might not fit into existing frameworks. They're following the evidence wherever it leads, even when it points toward conclusions that challenge fundamental assumptions about how physics works. This willingness to question basic assumptions and follow unexpected results is what drives scientific progress. Most of the major advances in physics have come from discoveries that initially seemed to contradict well-established theories. The antimatter research at CERN might be pointing toward exactly this kind of revolutionary moment in our understanding of fundamental physics. But even if the current mysteries turn out to have mundane explanations that don't require major revisions to existing theories, the research itself is advancing human knowledge in valuable ways. The experimental techniques being developed are pushing measurement science to new levels of precision. The theoretical frameworks being explored are revealing new mathematical structures that might have applications beyond particle physics. The international collaborations being forged are creating new models for scientific cooperation that could be applied to other global challenges. Perhaps most importantly, the research is training a new generation of scientists in ways of thinking that will be valuable regardless of what specific discoveries they make. The students and postdocs working on antimatter experiments today are learning to handle problems of extraordinary technical complexity and conceptual subtlety. They're developing skills in precision measurement, statistical analysis, international collaboration, and scientific communication that will serve them throughout their careers. Many of these young researchers will eventually move on to other fields, taking with them the problem-solving approaches they learned while studying the universe's strangest particles. Some will become leaders in technology companies, applying the precision and creativity they developed in fundamental research to practical engineering challenges. Others will become teachers, passing on to future generations the sense of wonder and intellectual rigor that drives scientific discovery. This human dimension of the research is often overlooked, but it might be its most important long-term impact. Scientific institutions don't just produce discoveries and technologies, they produce people who understand how to think clearly about complex problems, how to work effectively in diverse teams, and how to maintain intellectual honesty in the face of uncertainty and pressure. The antimatter research at CERN is contributing to this broader educational mission while simultaneously pushing the boundaries of human knowledge about the fundamental nature of reality. It's preparing the next generation of scientists to tackle challenges that we can't even imagine yet, while also working to solve mysteries that have puzzled humanity for decades. This dual mission of education and discovery is what makes institutions like CERN so valuable to human civilization. They represent our commitment to understanding the universe, not just for immediate practical benefit, but for the deeper purpose of satisfying our curiosity about our place in the cosmic order. The weird things happening with antimatter are reminding us that This cosmic order is far more complex and interesting than we ever suspected. Each new measurement reveals additional layers of mystery that require even more sophisticated experimental approaches to investigate. But this complexity isn't a barrier to understanding. It's an invitation to develop better theories, more precise instruments, and more creative ways of thinking about the deepest questions we can ask. The antimatter mystery at CERN represents one chapter in humanity's ongoing conversation with the universe. We ask questions through our experiments, and the universe responds through the data we collect. Sometimes the answers are clear and decisive. More often, they're subtle and ambiguous, requiring years of additional work to interpret properly. But this conversation continues regardless of how long individual mysteries take to resolve. Each generation of scientists builds on the work of their predecessors, asking more sophisticated questions and developing better tools for finding answers. The antimatter research happening now at CERN will inform the investigations conducted by scientists who haven't even been born yet. This intergenerational aspect of scientific research provides a sense of continuity and purpose that transcends the frustrations and uncertainties of any individual investigation. The current generation of antimatter researchers is participating in something much larger than their own careers or immediate research goals. They're contributing to humanity's greatest intellectual adventure, the ongoing effort to understand how the universe works at its most fundamental level. The questions they're investigating have fascinated humans for thousands of years, but only recently have we developed the tools to begin answering them through direct observation and measurement. The antimatter research at CERN represents one of our best opportunities to make progress on these ultimate mysteries, regardless of how long it takes to find complete answers. And that's perhaps the most important lesson from the weird things happening with antimatter at CERN. The universe doesn't reveal its secrets according to human timelines or expectations. Some questions might require entirely new experimental approaches that haven't been invented yet. Others might demand theoretical insights that no one has thought of, and some might remain mysteries for generations to come. But this uncertainty isn't a reason for discouragement. It's evidence that we're asking the right questions, pushing against the real boundaries of human knowledge. The fact that antimatter continues to surprise us, despite decades of sophisticated research, demonstrates just how much we still have to learn about the fundamental nature of reality. Every weird result, every unexpected measurement, and every puzzling observation brings us one step closer to discoveries that could transform our understanding of the universe. The antimatter mystery at CERN might eventually lead to revolutionary breakthroughs in physics, or it might reveal subtle aspects of reality that don't fundamentally change our theoretical frameworks. Either way, the investigation itself represents something remarkable about human nature and our relationship with the cosmos we inhabit. We're a species that refuses to accept mystery as the final answer to fundamental questions. We're willing to invest enormous resources and efforts in understanding phenomena that have no immediate practical application. And we're driven by faith that the universe, however strange and complex it might be, is ultimately comprehensible to minds like ours. That faith has been vindicated by every major advance in scientific understanding throughout human history. The antimatter research at CERN continues this tradition, pushing forward into unknown territory with the confidence that careful observation and creative thinking will eventually yield insights that are worth the effort required to obtain them. The story of antimatter at CERN is far from over. New experiments are being planned that will probe even deeper into these mysteries. New theoretical frameworks are being developed that might finally make sense of the accumulating puzzles. And new generations of scientists are being trained who will carry this work forward long after the current researchers have moved on. Whatever discoveries emerge from this ongoing investigation, they will represent another triumph of human curiosity over cosmic mystery. Another demonstration that we live in a universe that consistently surprises us, but that also rewards our efforts to understand it. And another step forward in the greatest adventure our species has ever undertaken, the quest to comprehend the fundamental nature of reality itself. The weird things happening with antimatter at CERN are forcing us to confront something uncomfortable. Despite building the most sophisticated machines in human history, despite decades of precision measurements, despite international collaborations involving thousands of the brightest minds on the planet, we're still missing something fundamental about how the universe actually works. Think about that for a moment. We can trap individual antimatter atoms using magnetic fields stronger than anything found naturally in the solar system. We can measure particle properties to 15 decimal places. We can transport antimatter across campus in specially designed vehicles. And yet the central question that started this entire research program remains stubbornly unanswered. Why does anything exist at all instead of just empty space filled with radiation? It's not that scientists haven't been trying hard enough. The amount of effort and resources devoted to antimatter research is staggering. The Large Hadron Collider alone cost over $10 billion to build and requires the combined expertise of universities from more than 40 countries to operate. The precision required for these experiments pushes human technology to its absolute limits. But here's what makes the current situation so fascinating. The data isn't saying there's nothing interesting happening with antimatter. It's saying the opposite. There are violations of fundamental symmetries. There are tiny asymmetries that shouldn't exist according to our best theories. There are hints that gravity might affect antimatter slightly differently than regular matter. The problem is that none of these effects are quite large enough to explain the cosmic mystery. They're all pointing in the right direction, suggesting that matter and antimatter don't behave as perfect mirror images of each other. But when you add up all the asymmetries that have been measured so far, they still fall short of explaining why the universe is dominated by matter. This situation is creating a strange kind of tension in the physics community. On one hand, researchers are genuinely excited about the discoveries they're making. The CP violation in lambda B baryons represents a real breakthrough in our understanding of particle physics. The successful transport of antimatter opens up experimental possibilities that didn't exist before. The gravity measurements provide the first direct tests of how antimatter responds to gravitational forces. On the other hand, these discoveries are revealing that the full explanation for the antimatter mystery is likely to be far more complex than anyone anticipated. Instead of finding one clear mechanism that explains everything, researchers are uncovering multiple subtle effects that might all contribute to the cosmic antimatter imbalance in ways that aren't yet understood. This complexity is both frustrating and encouraging. Frustrating because it means the mystery won't be solved quickly or easily. Encouraging because it suggests there are aspects of fundamental physics that we haven't discovered yet. And in science, the discovery of new phenomena often leads to advances that are far more important than the original questions that motivated the research. Consider what happened with quantum mechanics in the early 20th century. Physicists started investigating why heated objects glow with specific colors, a seemingly mundane question about thermal radiation. What they discovered instead was that energy comes in discrete packets, leading to a complete revolution in our understanding of matter and light. That revolution eventually gave us lasers, computers, medical imaging, and countless other technologies that define modern civilization. The antimatter research at CERN might be heading toward a similar kind of breakthrough. The scientists working on these experiments aren't just trying to solve one specific puzzle about cosmic evolution. They're developing new ways of thinking about symmetry, time, and the fundamental structure of reality that could have implications extending far beyond particle physics. The precision measurement techniques being pioneered for antimatter research are already finding applications in other fields. The theoretical frameworks being developed to explain symmetry violations are providing new approaches to understanding everything from quantum computing to cosmology. The international collaboration models being used at CERN are being adapted for other large-scale scientific projects. But perhaps the most significant impact is conceptual. The antimatter research is teaching scientists to look for effects that are almost impossibly small, but potentially cosmic in their consequences. This perspective is changing how researchers approach fundamental questions across all areas of physics. The idea that tiny violations of seemingly perfect symmetries could accumulate over billions of years to produce dramatic consequences is influencing research on dark matter, dark energy, quantum gravity, and the formation of large-scale structure in the universe. Scientists are learning that the universe might be full of subtle asymmetries and weak effects that only become apparent when you look carefully enough and wait long enough. This new way of thinking about physics is already generating predictions that can be tested through future experiments. Some theories suggest that the matter-antimatter asymmetry we observe might be connected to the mysterious dark matter that makes up most of the universe's mass. Others propose that the same mechanisms that create particle asymmetries might also explain why space itself is expanding at an accelerating rate. These connections between apparently unrelated phenomena illustrate why the antimatter research at CERN matters beyond its immediate goals. The experimental techniques, theoretical insights, and ways of thinking being developed to study antimatter are providing tools for investigating mysteries across all of physics and cosmology. The researchers working on these problems understand that they're not just studying exotic particles in isolation. They're exploring the fundamental unity that underlies all natural phenomena. The same mathematical structures that describe antimatter behavior also govern the evolution of stars, the dynamics of galaxies, and the quantum behavior of atoms. This unity isn't immediately obvious because different phenomena occur on vastly different scales of size, energy, and time. But the research being conducted at CERN is revealing deep connections between processes that seem completely unrelated. The forces that distinguish matter from antimatter might be related to the mechanisms that determine the structure of space-time itself. These connections are only beginning to be understood, but they're already suggesting new experimental approaches that could revolutionize our understanding of fundamental physics. The PUMA experiment, which will fire antimatter at unstable atomic nuclei, represents just one example of how antimatter research is expanding into new territories. By studying how antiprotons interact with exotic nuclear systems, researchers hope to discover new sources of asymmetry that might help explain the cosmic matter-antimatter imbalance. But they're also investigating whether these interactions might reveal new forces or particles that haven't been detected in other types of experiments. The debris produced when antiprotons annihilate with atomic nuclei contains information about nuclear structure that can't be obtained through any other experimental method. This information might provide clues about how matter behaves under the extreme conditions that existed in the early universe, when temperatures and densities were far beyond anything that can be created in terrestrial laboratories. But PUMA also represents something more ambitious. It's an attempt to use one mystery to investigate others. The same experimental setup that studies antimatter behavior will also probe the structure of unstable atomic nuclei, the dynamics of nuclear forces, and the properties of matter under extreme conditions. This approach of using one research program to advance multiple areas of science is becoming increasingly common at CERN and other major research facilities. The tools and techniques developed for specific experiments often find unexpected applications in completely different fields. The magnetic containment systems designed for antimatter traps, for example, are being adapted for fusion energy research, where scientists need to confine extremely hot plasma without letting it touch any physical surface. The precision measurement methods used to detect tiny particle asymmetries are being applied to gravitational wave detectors, where researchers need to measure changes in distance smaller than a fraction of the diameter of a proton. The data analysis techniques developed to extract tiny signals from enormous datasets are finding applications in fields ranging from medical, imaging to climate science to artificial intelligence. The international collaboration methods pioneered at CERN are being used as models for other global research projects, from astronomy to environmental science. But even if the antimatter research never produces any direct practical applications, it would still be valuable for its contribution to human understanding. The questions being investigated touch on the deepest mysteries of existence. Why does the universe exist in its current form? What determines the fundamental laws that govern all natural phenomena? Are there aspects of reality so subtle that we're only just beginning to glimpse them? These questions have fascinated humans for millennia, but only recently have we developed the tools to begin answering them through direct observation and measurement. The antimatter research at CERN represents one of our best opportunities to make progress on these ultimate mysteries. The scientists working on these problems understand the historical significance of what they're attempting. They're participating in humanity's ongoing effort to understand our place in the universe and the physical laws that determine everything from the behavior of subatomic particles to the evolution of galaxies. This perspective helps sustain motivation through the inevitable challenges and setbacks that accompany any ambitious research program. Antimatter experiments are extraordinarily difficult to conduct. The particles being studied exist for incredibly brief periods under highly artificial conditions. Equipment failures can destroy months of preparation. Theoretical predictions often turn out to be incomplete or incorrect. But these difficulties are part of what makes the research so valuable. Easy questions have already been answered. The problems that remain unsolved are those that require pushing human knowledge and technology to their absolute limits. The antimatter mystery represents exactly this kind of ultimate challenge. Every successful measurement, every technological breakthrough, and every theoretical insight contributes to humanity's growing understanding of how the universe actually works. The current generation of researchers is building on work that began decades ago and laying the foundation for discoveries that might not happen for many years to come. This long-term perspective is essential for understanding the true significance of what's happening at CERN. Individual experiments might not provide complete answers to fundamental questions, but they're contributing pieces to a puzzle that's much larger than any single investigation. The weird things happening with antimatter represent just one aspect of this larger effort to understand the deepest workings of reality. Other experiments at CERN and laboratories around the world are investigating dark matter, extra dimensions, quantum gravity, and dozens of other mysteries that challenge our current understanding of physics. Each of these research programs is contributing to a gradually emerging picture of how the universe works at levels of detail and precision that previous generations couldn't imagine. The antimatter research is providing crucial pieces of this larger puzzle, revealing how the most fundamental symmetries of nature might not be as perfect as scientists once assumed. The implications extend far beyond particle physics. If the basic symmetries that govern matter and antimatter can be violated, what does that say about other supposedly fundamental principles? How many other ironclad rules of physics might have subtle exceptions that become important under extreme conditions? These questions are driving the next wave of experiments at CERN and other research facilities. Scientists are designing tests to probe symmetries that have never been seriously questioned before. They're looking for violations so small that detecting them requires measurement precision that pushes technology to its absolute limits. But they're also developing new theoretical frameworks that can accommodate symmetry violations as natural features of the universe, rather than exotic anomalies. These new theories are suggesting possibilities that seem almost too strange to believe, but that might be necessary to explain the full complexity of how reality actually works. The process of testing such exotic theories requires experimental techniques that didn't exist just a few years ago. The ability to transport antimatter between buildings opens up possibilities for studying how these particles behave under different environmental conditions. The precision measurement methods being developed are revealing effects that were previously undetectable. The mobile antimatter transport system that worked so successfully is already being used to plan studies that would have been impossible before. Scientists are designing experiments to test antimatter behavior under different gravitational conditions, perhaps by taking it to higher altitudes where Earth's gravity is slightly weaker. They're investigating whether antimatter responds differently to various electromagnetic fields and cosmic radiation. These studies are pushing the boundaries of what's technically feasible with current technology. Maintaining antimatter stability during transport was challenging enough when it involved a carefully planned route across the CERN campus. Extending these capabilities to other locations and conditions presents entirely new sets of engineering challenges. But the potential scientific payoff is enormous. If antimatter behaves even slightly differently under different environmental conditions, that could provide crucial clues about why it's so rare in the natural universe. Maybe antimatter interacts with cosmic background fields in ways that regular matter doesn't. Maybe it responds to gravitational effects or quantum fluctuations differently than theoretical models predict. The precision required to detect such subtle effects is extraordinary. Scientists are working to measure differences that might be smaller than 1 part in a trillion, using particles that exist for fractions of a second under conditions that don't occur anywhere else in the solar system. The technical challenges involved are staggering, but so are the potential rewards. If researchers can identify the mechanisms that create matter-antimatter asymmetry, they won't just answer one specific question about particle physics. They'll potentially unlock new understanding of how the universe works at its most fundamental level. That understanding could lead to insights about dark matter, dark energy, quantum gravity, and the ultimate fate of the cosmos. But perhaps even more importantly, it would demonstrate something profound about human nature and our relationship with the universe we inhabit. We're creatures that emerged from cosmic evolution, using our evolved brains to study the very processes that brought us into existence. We're asking questions about the fundamental nature of reality using tools and concepts that are themselves products of that reality. The fact that we're capable of making progress on such deep questions, despite our obvious limitations as biological organisms that evolved for completely different purposes, suggests something remarkable about the structure of the universe itself. It implies that reality is not only comprehensible to minds like ours, but that the mathematical patterns underlying natural phenomena are elegant and beautiful enough to be discovered through careful observation and creative thinking. This relationship between human consciousness and cosmic structure is one of the deepest mysteries in all of science. Why should the universe be comprehensible to creatures like us? Why should the mathematical tools developed by human minds over the past few centuries be so effective at describing phenomena that occur on scales ranging from subatomic particles to galactic clusters? The antimatter research at CERN is contributing to our understanding of this mystery in ways that extend far beyond the specific questions about particle physics that originally motivated the investigations. The precision and sophistication required for these experiments are revealing new aspects of what human minds can accomplish when they're focused on fundamental questions about the nature of reality. The international collaboration required for antimatter research is also demonstrating something important about human nature. Scientists from dozens of countries, representing different cultures, languages, and educational traditions, are working together on problems that transcend all national boundaries and cultural differences. They're united by curiosity about questions that are equally mysterious and compelling to anyone who thinks seriously about the nature of existence. This collaborative spirit is essential for making progress on problems that are too complex for any individual or single institution to solve alone. The antimatter mystery requires expertise from multiple fields of physics, engineering capabilities that push technology to its limits, and theoretical insights that build on centuries of accumulated knowledge. But the collaboration also represents something deeper about human values and priorities. In a world often divided by political conflicts and economic competition, the antimatter research at CERN stands as an example of what we can accomplish when we work together toward common goals that benefit all of humanity. The knowledge being generated through this research doesn't belong to any particular country or institution. It's part of humanity's shared understanding of the universe we all inhabit. The discoveries made at CERN will eventually find their way into textbooks read by students around the world, regardless of their nationality or cultural background. This universal character of scientific knowledge is one of its most important features. Unlike many other human activities, scientific research generates insights that are equally valid and valuable everywhere. The laws of physics that govern antimatter behavior at CERN are the same laws that operate in distant galaxies billions of light years away. This universality provides a foundation for international cooperation that transcends temporary political differences. Scientists working on antimatter research today are contributing to a body of knowledge that will be used by future researchers, regardless of what political or economic changes occur in the meantime. The long-term perspective required for fundamental physics research helps maintain focus on goals that extend beyond immediate practical concerns. The antimatter mystery has been puzzling scientists for decades, and it might take many more decades to solve completely. But the investigation continues because the questions being asked are too important to abandon. Every measurement, every successful experiment, and every theoretical insight brings us closer to understanding why the universe exists in its current form rather than remaining an empty void. That understanding represents one of humanity's greatest intellectual achievements, regardless of whether it leads to immediate practical applications. The weird things happening with antimatter at CERN are reminding us that the universe is far stranger and more complex than our everyday experience suggests. But they're also demonstrating that this strangeness is not beyond human comprehension. With sufficient care, creativity, and persistence, we can uncover the deepest secrets of reality itself. The antimatter mystery might eventually lead to revolutionary breakthroughs that transform our understanding of fundamental physics, or it might reveal subtle aspects of reality that don't fundamentally change our theoretical frameworks. Either way, the investigation itself represents something remarkable about what it means to be human in a universe that continues to surprise us at every turn. We're a species that refuses to accept mystery as the final answer to fundamental questions. We're willing to invest enormous resources and effort in understanding phenomena that have no immediate practical benefits. And we're driven by faith that the universe, however strange and complex it might be, is ultimately comprehensible to minds that are determined enough to keep asking questions and clever enough to devise ways of answering them. That faith has been vindicated by every major advance in scientific understanding throughout human history. The antimatter research at CERN continues this tradition, pushing forward into unknown territory with confidence that careful observation and creative thinking will eventually yield insights that justify the effort required to obtain them. The story unfolding at CERN right now is far from over. New experiments are being planned that will probe even deeper into these mysteries. New theoretical frameworks are being developed that might finally make sense of the accumulating puzzles. And new generations of scientists are being trained who will carry this work forward long after the current researchers have moved on. Whatever discoveries emerge from this ongoing investigation, they will represent another triumph of human curiosity over cosmic mystery. Another demonstration that we live in a universe that consistently surprises us, but that also rewards our efforts to understand it. And another step forward in the greatest adventure our species has ever undertaken, the quest to comprehend the fundamental nature of reality itself. The weird things happening with antimatter at CERN are just the beginning. Each strange result, each unexpected measurement, and each puzzling observation is opening new doors to understanding. Behind those doors lie answers to questions that have fascinated humanity for millennia. Questions about why anything exists, how the universe came to be the way it is, and what role consciousness plays in the cosmic order. We may not have those answers yet, but we're closer than we've ever been before. And that proximity to ultimate understanding is perhaps the most exciting thing of all about the current state of antimatter research. We're living through a time when the deepest mysteries of existence might finally yield their secrets to human investigation. The universe has been keeping its secrets for nearly 14 billion years, but at CERN, those secrets are finally starting to whisper their truths to anyone willing to listen carefully enough to hear them.